Organometallic reagents are powerful bases. So this is the first of the organometallic reagents reactions. So a little bit about acids and bases. If again, before we begin, if you're still not sure about the reactions of acids and bases, I highly recommend that you review acid-base reactions. All you have to know about acid-base reactions is that, at least in this case, is that bases attack protons, H's. So this H right here. And obviously you must have a base to attack that proton. So in this case, your Grignard reagent, in this case, is going to act as the base. And this is going to be your acid. Water has a pKa around 15. So it's moderately, it's weakly acidic. So here's how the reaction is going to take place. So this is going to attack the proton. And of course, the electrons are going to go back to the oxygen. Very well. So then the product would become CH3, CH2, and watch what I'm going to do. I'm going to attach that H that we just added. So imagine I just replaced this bond between the C and the MGBR with an H. So it's CH2H instead of CH2MGBR. Plus, of course, HO. I'm going to list it this way. MGBR. Okay. Which, by the way, HO is from the OH minus. The reason why I wrote it this way so that we can see the negative is obviously, here it is, O minus. Mg has a +2 charge, and Br has a minus. So the charges cancel out. 2 negatives and 2 positives. So the pKa of the conjugate acid in this case would be 50. And if you recall from acids and bases that we studied last semester, we always shift toward the weaker acid, So this is a weaker acid. Very well. The same thing can be done with the organolithium. So where do you think the organolithium is going to attack? Which proton? It is this one. Yep, so there's an H. I mean, we're showing it. So this is a base. This is the acid, carboxylic acid. And of course, we have O minus, Li plus, which sometimes is written as OLI. So either one is acceptable, but you have to understand why, because again, of the charges. So the rapid reaction with water or any protic means that Grignard reagents, organolithium reagents, and cuprates cannot be prepared from compounds that contain acidic groups because there will be interferences. So these are acidic groups that you need to keep, commit to memory or just recognize them. OH, you know, an acid has an OH in this case, like in the carboxylic acid, even water can act acidic, sulfuric, nitric acid, etc. NH2, amines, sulfides, etc. So I wrote a statement here beforehand so we can just streamline the process. So make sure you copy this. Do not make a Grignard or organolithium compound from compounds that contain these groups. I'll show you why. Because you will end up with what we call a failed synthesis. So write down this statement, and then let's show you an example. So if I start with this, oops, we know that the magnesium is going to insert itself, so it's going to be this. MgBr. Now, the problem arises is when you make this and then an interaction happens in the following way. So let's say we have another one of these, so the starting material, and let me just line it up in a so look what's going to happen now. You have the organometallic, the Grignard reagent, and you have an acidic group. Basically, this is going to happen again. But of course, we don't have water. We have this end, which is an alcohol, the end of this alcohol. So what's going to happen is, instead of making more and more of these organometallic Grignard reagent, no, there's going to be an acid-base reaction. And you're going to make this chunk right here. It's going to come down with an H added. So it's going to be HOCH2CH3. So this proton was gained. Here it is. Plus what's left over. So you have O minus CH2Br. Of course, the MgBr will be zero. So this is a problem here, is that we're not going to make enough of the organometallic here. And we will, again, the interference is going to happen at this end, and then we can't prepare this for nucleophilic, for a nucleophile. So this is no longer nucleophilic. No longer nucleophilic. So the reaction will stop. It's just a methyl now. There's no electron-rich atom anymore, that electron-rich carbon anymore. As far as the next thing we say in this statement, the rapid reaction with water or any protic acid can be used synthetically to turn an alkyl halide, right here, into a hydrocarbon, or to convert an alkyl halide into a labeled hydrocarbon. I'm not going to discuss the latter part. I'm going to just to show you the first part here, the former, which is how to turn an alkyl halide into a hydrocarbon. So if we have this alkyl halide, and if we have magnesium and ether, which you are going to be doing a reaction on in your lab. So we know what's going to happen. The Mg is going to insert itself between the C and the Br. So we're going to have CH2 MgBr. Oops. Okay. So guess what? If we just add water, then we actually went from an alkyl halide, which is Rx, that's what we have, correct? Br is in halogen, to a hydrocarbon, to an alkane. So that's one great way of turning alkyl halide into an alkane. Alkane, at least in this case, or any other hydrocarbon, a pure hydrocarbon, or there are no functional groups, at least in this case, no heteroatoms. So that's the deal here.